Progress. Listo. Estamos viendo un poco de los sistemas operativos distribuidos. Esto inicialmente arrancó con los sistemas distribuidos. Ya se habló, recordando un poco de cómo son los sistemas operativos, cuáles son los principales sistemas operativos. Estamos viendo un poco de qué era el microkernel, el kernel, cuáles eran las diferencias del uno y del otro. Y uno de los ejemplos clásicos para hablar de microkernel es un sistema operativo llamado Minix. Como ya les estaba hablando en una ocasión, quien es un exponente importante dentro de este ambiente de los sistemas operativos distribuidos es Andrew Tannenbaum, que es el autor de algunos libros de sistemas operativos distribuidos, sistemas distribuidos, y ha aportado bastante dentro de los sistemas operativos. Es un gran exponente dentro de estos sistemas operativos. Algunos sistemas se basan en las investigaciones que él ha realizado. También recordemos que los sistemas operativos hay varios tipos. Hay sistemas operativos basados en red, sistemas operativos distribuidos, eh, sistemas operativos con servicios de red. Entonces, para sistemas de archivos, entre los sistemas de archivos está el Google File System. Pronto hablaremos de eso, si nos alcanza el tiempo. Y hoy vamos a escuchar una charla directamente de Andrew Tannenbaum de Minix, basado en el microkernel. Entonces, en la clase anterior estamos revisando un poco de la diferencia de un kernel y un microkernel. Para resumir, pues vimos que el microkernel, como su palabra lo indica, es más reducido. A esto, esto se debe a que las funciones quedan bastante reducidas en el microkernel, a diferencia del kernel. Tiene muchas más funciones, mucha más funcionalidad, y lo puede separar en el modo kernel. Entonces habían dos modos, modo kernel y modo usuario. Entonces toda esta funcionalidad la gobierna, la tiene segura y está en poderío del kernel. En cambio, en el microkernel no tiene mucha funcionalidad, a diferencia del otro. La otra cuestión es que cuando estamos hablando de sistemas operativos con microkernel, pues es mucho más liviano, mucho más ligero, podríamos ponerlo en cualquier lugar. Sobre todo en la parte de los sistemas embebidos, tarjetas, Raspberry, Arduino o cualquier otra cosa más, podríamos montar. Entonces, sin más preámbulos, veamos el video. En cualquier momento ustedes pueden levantar la mano, hacer preguntas, levantar el micrófono o poner la pregunta en el chat. Ya les paso el charla.
Okay, I'm about to introduce a guy who doesn't need an introduction.
Por cierto, pues la charla está en inglés, pero está subtitulada. Entonces pongamos atención en el subtítulo. Están en un congreso que se llama Frostcom. Ahí dice Sistemas Operativos Libres, dice Fried and Open Source Software Conference. Entonces, una conferencia que se le hace anual en cuanto a los sistemas operativos libres. Sigamos.
Many remember him from some news group post like many, many years ago. Most of you will own at least one book of him. And I present to you Andrew Tannenbaum.
La traducción es Andrew Tannenbaum. Por eso la traducción lo pusieron 10 bar, pero es Tannenbaum. Ahí está, tuvo un error en la traducción.
Thank you, but wait, maybe you won't like the talk. Okay, I'm going to talk about Minix 3. Currently, the mode is a re-implementation of NetBSD using a
Por cierto, Minix va por la versión 3. Es código abierto y todo el mundo puede aportar.
microkernel, and I'm, Andrew Tannenbaum, but my students did all the work, actually, my programmers. Okay, the goal of the project is to build a reliable operating system. So let's start with my definition of a reliable operating system. Okay, an operating system is said to be reliable when a typical user has never experienced even a single failure in his or her lifetime and does not know anybody who's ever experienced a failure. Okay.
Eso es profundo y eso se ve típicamente en las clases de programación, que es confiable. Entonces, bastante anecdótico lo que están leyendo.
In engineering terms, this probably means something like mean time to failure of like 50 years. I don't think we're there yet. Let me describe what I think of as the television model. Okay, at least old style TVs, it's getting less so. You buy the television, you plug it in, and it works perfectly for the next 10 years. Okay? Now let's look at the computer model. Windows Edition. Okay, you buy the computer, you plug it in, now we're 2/3 of the way there. Okay, it's just this little part about it works perfectly for the next 10 years. That's a little bit different. First you install service packs 1 through 9F. Then you install 18 new emergency security patches that happened after 9F. And then you find and install 7 new device drivers. And then you install the antivirus software. Then you install the anti-spyware software. Then you install the anti-hacker software. Then you install the anti-spam software. Then you reboot the computer. Okay? But I'm not done yet. I just ran out of space on the slide. So there's more. It doesn't work. See, you call the help desk, okay? You wait on hold for 30 minutes. Okay? They tell you to reinstall Windows, which is what you're trying to do in the first place, okay? The typical user reaction to this is something like this. I saw a story in the New York Times which said that 25% of computer users have actually gotten so angry they hit the computer. Most of them don't know where the computer is, though. This is the monitor, which is not where the problem is. Anyway, so you might say, is reliability so important? Who cares if it works or not? It's annoying when it doesn't work, and you might lose some work if it goes down. But also think about other situations like industrial.
Un pequeño error. Ya, listo. Pensaba que no está siendo grabado, pero aquí sí está siendo grabado. Sigamos.
Process control systems in factories. Think about power grids when their computer doesn't work. Think about hospital operating systems, hospital operating rooms when the computer doesn't work. Think about banking and e-commerce servers. What happens if that doesn't work? Or emergency phone centers, or control software in cars and airplanes and places like that. So there are places where it actually matters whether it works or not. Okay. So the question is it feasible? Is it possible to make software, and hardware that works? Well, first of all, we won't find out if we don't really try. And so the Dutch Royal Academy gave me 2 million euros to try. So I said, thank you very much, we'll try. And then the European Union, I have an ERC advanced grant, if you know what that is, for 2.5 million euros to give it a shot. So we're trying. Okay, thank you very much, Royal Academy, and thank you very much, European Research Council. The first question is reliability achievable at all? Is this even possible? Well, systems can actually survive hardware failures. For example, RAIDs can survive a failed disk. The disk dies, and if your RAID is properly working, the system merrily continues even with a dead disk. There's some redundancy in there, and there's parity, there's algorithms, RAID 1, RAID 2, and so on. You can survive a failed disk if configured properly. ECC memory can survive parity errors in memory because they have, that redundancy basically using a Hamming code, and they can survive memory errors. TCP/IP can survive lost packets because there's an acknowledgement algorithm, and if you send the packet, don't get an acknowledgement, you send it again, keep doing it until you get an acknowledgement. So, you can do that. CD-ROM drives, CD-ROM blanks and DVDs and Blu-rays, about 3/4 of the bits are actually error-correcting bits. It's a very complicated scheme where they use 14 bits to code 8 bits, and then there's these 2K sectors, and it's multiple levels of redundancy, so they can recover from a very large number of errors, because the disks are stamped mechanically. It's not that bad. Maybe it is, I don't know. You can recover from hardware errors in many areas. So, you think that software errors ought to be doable if you can recover from, fatal hardware errors. This requires organizing your software a little bit differently, okay? So I think operating systems research, which is sort of, community I'm in, needs to be refocused a little bit. We have basically nearly infinite hardware on PC class machines. An ordinary PC buying those through now, it's got, compared to like where we were 10 or 20 years ago, this is basically infinite, okay? There's lots of CPU cycles, there's lots of RAM, there's lots of bandwidth. Current software has tons of useless features that nobody wants, having to do with the economics of the software business, of, version 14 has to have more features than version 13, even nobody has used any feature beyond version 7, but they gotta add new features because that's the way they sell it, okay? So the software is slow and bloated and buggy. And, to achieve what I would call the TV model, I think future operating systems need to be changed somehow. They have to be smaller, they have to be simpler, they have to be modular, which is very important, they have to be more reliable, and they have to be secure. And I think self-healing. I think self-healing is a key word. They have to look for their own errors and try to fix them on the fly. And that's what our research has sort of been focused on. Let me give you a very brief history of the work we've been doing for about, I don't know, since 1987, I think. 1976, a professor named John Lyons at New South Wales in Australia wrote a book on Unix version 6. When version 6 came out, he wrote this commentary on it, sort of like commentaries on the Bible or something. And then AT&T, in its brilliance, when it came out with, version 7, had a clause in there saying, "Thou shalt not write a book about version 7." God forbid that students all over the world learn about their product. We cannot tolerate this. So they did that. In '85, I said maybe I could rewrite, Unix on my own, all by myself. I was young and crazy. I didn't know that it was hard. So I did it. It took me 2 years. Long stories about that, but. So I wrote it, and then I wrote a book about, the software, and we released it, and it was free of AT&T code, and so all the source code was out there, and people could do whatever they want with it. There was some minor licensing initially, but basically it was available certainly to universities and for non-commercial use. In '97, came out with another version, version 2, and a new book, and this was POSIX rather than version 7 compatible. And then 2000, we changed the license. The publisher, Prentice Hall, I had arguments with them, but they didn't understand software. Finally, in 2000, they gave up and said, just use the BSD. I said, I wanted to use the BSD license. And they said, we don't know what it is, but do it. 2004, I started working on this reliable, stuff. 2006 was the 3rd edition of the book with Albert Woodhull. 2008, I got the European grant. And then we really started, I could hire programmers, and it got, more serious at that point. And then the focus started moving toward embedded systems. So there's, and then we moved toward NetBSD compatibility. Some of you may know that Linus Torvalds was one of the first Minix users and began changing it and changing it and changing it. Pretty soon, he had his own system. So to some extent, Linux is kind of a fork of Minix. Okay, there were 3 editions of the book. I think the cover got better as time went on. Okay, let me talk about intelligent design, at least as applied to operating systems. Minix is a microkernel. It's got about 15,000 lines of code. Most of them are C, a little bit of assembly code. And Linux has got 15 million lines. Windows is probably above 100 million lines now. It's really pretty bad. People have done studies of bugs, in companies, there are bug repositories and whatnot. And, 1 bug per 1,000 lines of code is about the best you can do with really, state-of-the-art techniques and, code reviews and all things. If you can get down to 1 bug per 1,000 lines of code, you've done pretty well. If you got 15 million lines of code or 100 million lines of code, you do the arithmetic. Now, not all the bugs are serious. There may be spelling errors in messages and stuff, but some of them are always serious, right? I mean, these things are getting patched all the time because, so Minix has got, maybe 15 kernel bugs. Linux has got, 15,000. Windows has got, a million. There's a lot of bugs out there. And drivers, typically, if people have studied this, have 3 to 7 times more bugs than everything else, because everybody wants to study the memory management code, and nobody wants to study, the Epson 2156 printer driver, which is, enormously complicated, et cetera. And, 70% of the code is the drivers, and nobody ever looks at that. So although open source, in theory, people can look at it, in reality, nobody ever does. And in Windows, nobody has the code except for Microsoft, and they're too busy. So I think what you need is like highly modular systems. You need the operating system to run basically as multiple user mode processes, not in the kernel. These things separated from each other. And so step one is to isolate the components very well. Okay, so move all the loadable modules and everything except the very, very hardcore kernel out of the kernel into user space. Okay, and that means all the drivers out, all the file systems out, memory management code out. Run everyone out with as a separate process using the POLA, the principle of least authority. That is, don't give a component any more power to do damage than it actually needs to do its work. And we'll come back to that a little bit later. It's the principle of least authority, very important principle. Step two is isolate the I/O. Isolate all the I/O devices. Limit access to the I/O ports. In a conventional everything in the kernel system, the audio driver has access to the disk. It's not supposed to, but technically, if it wants to, it can write on the disk. That has to be prohibited by putting each driver in a separate user mode process and restricting access to the I/O ports. You got to constrain the DMA, so you can't DMA over somebody else's memory. Then you got to isolate the communication. You got to limit inter-process communication. You have to restrict the kernel calls on a per component, need to use basis. You got to restrict the inter-process communication. Not everybody can talk to everybody, but you can only talk to those other components that you need to talk to get the work done. Make sure that a faulty receiver can't hang a faulty sender. So if A sends a message to B, and then A doesn't wait for the reply, you don't want to hang B. So here's the architecture of Minix 3. Okay, in the kernel, running in the actual kernel of the kernel on the bare metal is the microkernel. It handles interrupts. It handles process scheduling. It handles inter-process communication. It does not handle any of the device drivers. It does not handle memory management. It does not handle anything else. It's very, very bare bones stuff. That's still 15,000 lines of code. Okay, but that's just you're going to make all the I/O devices. So there's stuff you got to make work. When an interrupt happens, certain things have to happen next, so it can do the next step, and the registers have to be saved, and it turns out there's a lot of that stuff. Okay, and there's a little bit of scheduling you have to do at the bottom. You got to manage the MMU. There's some stuff you got to do in the kernel, but it's only about 15,000 lines of code if you're careful. And L4, which is a comparable system, is also about this size, somewhere in the 15,000 line thing. The next level, which are all user mode processes, are the I/O devices. Okay, so the disk driver, the terminal driver, the network driver, the printer driver, all the drivers, each one runs as a separate user mode process with the MMU turned on. It's limited, what it can do in terms of accessing physical, resources and so on. Then at the next level are the servers, which are sort of the real operating system, the file server, possibly multiple ones, process server, memory servers, things that actually are what we normally think of as the operating system, each running as a separate process. And the top layer are just the regular, POSIX programs, okay? So this is sort of the architecture of the system. Now, user mode device drivers. Each driver runs as a user mode process, protected by the MMU. It doesn't have any super user power, just a regular old user process, okay? It's protected, the MMU is turned on, so it can't get out of its address space. It does not even have access to the I/O ports. So the disk driver can't even write on the disk. It's got to ask the kernel. It's going to make a kernel call saying, here's a bunch of registers, here's a bunch of values, go write these values in those registers. The kernel first checks, is this allowed? And if it's allowed, it does it. If it's not allowed, it gets back an error message saying no permission. So the disk driver can write on the disk, but if the audio driver tries to write on the disk, it gets back an no perm message and it can't do it. The servers are in user space. Each server runs as a separate process. Some of the key servers are the virtual file server, so you can have multiple file systems. There's the actual file systems. There's the process manager, does most of the work managing processes. The memory manager figures out, who goes where in memory. There's the network server. There's a thing called the reincarnation server, which I'll come to later, which is an interesting little beast. It brings back the dead. Here's a simplified example of some of the stuff. So here's what happens if you try to read something from, your read system call, POSIX call, and you're lucky because the block you want happens to be in the file system's cache, okay? So the user makes a call to the file system. That little colored thing under FS, that's the file system's cache. File system checks, is the block I need in the cache? No, if it's lucky, the answer is yes. And it calls the kernel and says, go copy that block to the user, copies the block to the user, and everybody's happy, okay? So that's the easy case. The harder case is the block is not in the cache, okay? So now the user calls the file system calls the disk driver saying, go read that block and put it over here. The disk driver, calls the kernel saying, I want to do disk I/O, here are the parameters, checks it, if it's valid, it turns the disk on. Okay. A little bit later, the actual drive sends a note, does an interrupt basically, but at a very low level, that's turned into a message. So we get rid of interrupts at a very low level. A message comes into the disk driver saying, hardware interrupt. And then the disk driver goes and reads the registers, finds out, if it worked, and then eventually reports back to the file system saying, read completed correctly or there was an error. And then the user is informed and the copy is done into user space, okay? So all these are separate processes, and there's a little bit of overhead here. It's like a microsecond. I haven't timed it recently, but it's less than a microsecond of overhead. So there is, some overhead in the process. But if you're reading from the disk, that's milliseconds, okay? Even an SSD is 100 microseconds. So a couple more microseconds here or there isn't going to be the real killer. Now, what does the reincarnation server do? It's the parent of all the drivers and servers. So it's like up there, when the system boots, and I think it's the parent of, it's in the etc RC file. So before you start forking off all these servers and drivers, it runs. It's the parent of all the, the things, of the servers and drivers. And if something dies, it collects it. It's the parent, okay? And what does it do if some piece dies? It looks up in a table saying, what am I supposed to do? And the table typically will say, log it somewhere, maybe send an email to the administrator, and then try to restart it, okay? And if it's a driver, it'll go to the disk and go get the driver and start a fresh copy. You might ask, what if it's a disk driver? Well, we're clever enough to keep the disk driver in RAM all the time. So if the disk driver dies, take the RAM copy and put it in. And once we have a working disk driver, we can read the rest of them from the disk, okay? And it also pings the various servers, all the time. So the reincarnation server will say to the disk driver, hi, disk driver, how you doing? Disk driver will say, great, I did 62 reads in the last second. And then a little bit later, pings the disk driver again, how you doing? And it says, great, I did 104 requests in the last second. Okay? A little bit later, pings it again, says, how you doing? Then it says, disk driver, how are you doing? All right, I'll give you one more chance. How are you doing? At this point, the reincarnation says, not doing well. Kills it, goes and starts a new one, and the new one, is okay. The other components are told something happened. So if the file server, was waiting for a request to be completed, it has to record in its tables where it was, okay? And then it's told where the new one is, sends a message to the new one saying, go do the command again. So the commands have to be sort of idempotent in order to make this work. But basically, it's doable with a little bit of structuring. So, you can't make it transparent to everybody, but you make it reasonably transparent, okay? So disk driver recovery sort of looks like this, basically. So user calls the file system calls disk driver. Now this driver crashes, okay? So the reincarnation server hears about that because it gets sort of the equivalent of a sig no child, or it's all, and it says, oh, I'll start a new one, tells the file system about it, that the driver crashed, your problem. File server has saved the message it sent to the disk driver, says, oh, there's a new one, send the new one the message, and then hopefully the new one does the work and everything's fine. If the new one doesn't do the work, the process will repeat itself long enough until the work finally gets done, okay? If it's a really hard, a hard error, there's something, very, very wrong with the code, it probably can't recover. But our experience and everybody's experience is most errors are transient. There's some weird timing combination that causes things to fail. If you run it again, probably it won't happen again. Most errors are sort of transient. And so this is the whole point about a self-healing system. It detects its own errors, and it can correct the errors on its own on the fly. So this is the kind of property we want to have in the system, where you can detect and correct your own errors. In the same way, for example, TCP, we'll send the packet out, it'll start a timer. If it hasn't got an acknowledgement when the timer goes off, it says, oh, there's a problem, take the recovery action, send it again. That's an example, of doing this in software for the operating system. And so we've tried to use that as kind of our model, okay? So some of the issues about reliability and security. Well, fewer lines of code means fewer kernel bugs. So we don't have as many bugs in the kernel as everybody else because we got less code. I'm not claiming a better rate, but I'm just claiming less code. 15,000 lines of code means a smaller trusted computing base. There's no foreign code in the kernel. It's only our code. On other systems, if you get a driver, you have to install a driver written by some kid in Taiwan whose boss was breathing down his neck saying, we got to ship, we got to ship. And the kid says the code's not ready. And the boss says, I don't care, we got to ship. Okay? That doesn't happen in Minix because there's no kernel, there's no driver code. You get some user process, won't work, but the kernel isn't affected by installing a new driver. We've also been fairly careful about static data structures. There's no malloc in the kernel, which means you sometimes have to over-dimension things, but RAM is cheap. And so, we don't have all the problems with malloc and, memory leaks and all that stuff. We don't have that because we don't have any dynamic stuff in the kernel. Moving bugs to user space, is what we're doing, doesn't make them fewer bugs, but it means they're less powerful bugs. Because if you're a bug in an audio driver, or worse yet, you're, a hack in an audio driver, somebody's compromised you, you can make very strange noise, but you can't fork off a new shell because when you try to create a new process, the kernel says, hey, audio driver, you have no permission to create other processes. Sorry, no perm, you can't do it. And so we reduce the power of the bugs. Okay. Fixed length messages, all the messages are 64 bytes, so there's no buffer overruns. You can't have all the problems with buffer overruns. There's a variable length messages, we don't have them. It's a hard constant, in one of the header files saying buffers are 64 bytes, messages are 64 bytes. We had a rendezvous system that A, sent to B, B listened and got the message, we copied it over. But it turns out that has some reliability issues. Namely, if the sender sends it to the, say the client sends it to the server is trying to do it, the client dies, the server can't respond and everything hangs. So we had to go to an asynchronous scheme, even though we like the rendezvous better because there are no lost messages, there's no buffer management. So we had to add asynchronous messages, but we try to avoid using it as much as we can. And we've integrated interrupts and messages, so at a very, very low level, interrupts are turned into messages. Okay. The untrusted code, like drivers, is heavily, protected by the MMU. So our model is, most of the operating system actually is untrusted code. That's kind of a different model than everybody else. So bugs and viruses and whatnot can't spread from one module to another module easily because we assume our starting position is that the most of the operating system is untrusted code. The kernel is trusted, but that's very small. Okay. Nobody can touch kernel data structures to muck them up. Nobody has permission to write on the kernel. If somebody needed to read the kernel data structure, I think we have a couple of system calls where you could read it and simply copy it into your address space, but you can't write it. Okay. So a lot of the problems if somebody mucks up, a kernel data structure and you're hung, can't happen. Bad pointers, a bad pointer could crash a driver or one component, but it can't crash the kernel because it can't, get at the kernel. Infinite loops can be detected if some component is looping and not, paying attention and doesn't answer the ping from the reincarnation server. That's effectively dead, okay? And then it'll be killed and a new one will be started. Okay. I should say that starting things is tricky when there's state, and we're working on that to some extent, but we haven't solved that problem entirely yet. But things that are stateless, and most drivers are stateless, that we can deal with. We just start a fresh copy, okay? But I'll talk more about, state later. So we're restricting the power of bugs to do damage rather than reducing the number, okay? Okay, other advantages of user drivers, well, it's a shorter development cycle. You do something to the thing, you compile it, you run it, doesn't work, okay. You can just start a new one. You don't have to reboot the computer, which takes, 5 minutes. So it's a normal programming model. You start up a process that doesn't work, and you can debug it. There's no crash time, there's no reboot. You can use normal debugging type tools. It's just another process, okay? So it makes the whole cycle easier, it's more flexible. We ran a couple of one of my students ran some fault injection experiments. We injected 800,000 faults into each of 3 Ethernet drivers. This is done on the binary drivers at runtime. So, a debugging program overwrote memory. And we were careful about writing over, we didn't write random numbers into it. We looked for like branch less than, and we changed it to branch less than or equal to. And that's the kind of error a programmer might make. So we looked for specific errors that programmers might make, and we modified the binary to emulate the kind of errors that actually happen. And we inject 100 faults. We waited 1 second to say if it crashed, if it didn't crash, we inject another 100 faults, and we just keep going, okay? And we managed to crash drivers 18,000 times, excuse me, but we never lost the operating system, okay? Drivers went up and down all the time, but we never lost the operating system. That's the fault tolerance that I think is so important, okay? A little while back, I got a second ERC grant, and that was about sort of trying to make this thing more useful to the outside world. And we ported Minix to the ARM, okay? And so we had to restructure the source tree for multiple architectures. Oddly enough, we had that in Minix 1, but it sort of got lost along the way somewhere. We changed the booting to use U-boot for the ARM. We had to rewrite the low-level code dealing with the hardware because, the MMU works a little differently than the x86. We had to change the code for context switching. Some of the very low-level stuff is different on the ARM than the x86, so we had to change some of that. We got rid of the segmentation code since I think Intel has also lost interest in it, and ARM doesn't have it, so we threw it out. We gradually began importing the NetBSD ARM headers and libraries because, NetBSD is fanatic about portability. They really want to make things run on every known platform. So they've really been very careful not to do things like put inline x86 code in the middle of a C program. They don't do that kind of stuff. So it was nice and clean. We had to change the build system to do cross compilation because we didn't want to build it on an ARM. We wanted to build it on something else. We wrote drivers for the SD card and some of the other Beagle devices. And our initial target was the BeagleBone and the BeagleBone Black. And for those of you who don't know it, it's a PC with an ARM on it about the size of a smartphone, small smartphone, okay? And here are some of the characteristics of the Beagle. It's got an ARM v7. For those of you who know it, but the ARMs, the clock runs at 1 gigahertz. It's got half a gig of RAM in it. It's got 4 gigs of disk in it, flash memory. It's got HDMI port at 1080p. It's got 92 I/O pins. You can connect anything you want to have it drive things in embedded systems. 100 megabit Ethernet. It's got a USB port on it. It's open source, which is important. And about $45, maybe $55, depending on which model exactly. There's a couple of models out there. Some of you may know about the Raspberry Pi. If you compare it to the B+, that's got an ARM v6, which is an older and somewhat, less good processor. It's at 700 megahertz. Also half a gig. Doesn't have any disk memory. Doesn't have any disk on it. So that's a problem. It's also got 1080p. It's got 40 I/O pins, 100 megabit Ethernet. It's got 4 USB ports, which is a plus. On the Beagle Black, you'd need a hub if you wanted to go to more than one. It's not open source, so that's the main reason we didn't want to touch it. And it's a little bit cheaper. Okay. Okay. So I'm willing to admit I'm wrong. I've been right a lot, but I've been wrong once in a while. On January 29th, 1992, I posted to comp.os.minix. Don't get me wrong. I'm not unhappy with Linux. It'll get all the people who want to turn Minix into BSD Unix off my back. So I apologize. And actually, I do want to turn Minix into BSD. It just took me 20 years to realize it. I'm sorry about that. I'm kind of slow on the draw here. So Minix meets BSD. And the BSD thing is copyright Marshall Kirk McCusick and used by his permission. Okay, or maybe. So why BSD? Minix didn't have enough application software, and BSD is proven, reliable, quality product, and I think the code quality in general is better than Linux. Those guys are really fanatic about good code quality, and they don't release things, it's very slow release scale. I mean, there's once in a while there's a new release, and they really test it pretty carefully. It's a little bit different philosophy than Linux. Package Source is a really good package manager, and so we really like that, and there are thousands of packages out there. And there's an active community, and also license compatibility. That I was keynote speaker at Linux conference in Australia a few years ago, and I didn't mention licensing in the talk. Somebody asked me afterwards, what's the license? And I said, it's BSD license. And the audience began cheering. It's a Linux conference. So, I don't know. So anyway, we're BSD. Why NetBSD? Because it's got a tremendous emphasis on portability. You know, some of the other guys care about security, and but the NetBSD guys care about portability. If you're running it on 80 platforms, you can't have any weird stuff that uses some peculiar feature. You know, it's undocumented on the x86 that doesn't fly in 80 platforms. So they've really made an effort to make it really, really clean code. So we kind of appreciate that. So anyway, there's a bunch of features from NetBSD. We have the Clang LLVM compiler. That's a very nice thing. Some of you may know that Linux is not written in C. It's written in GCC. And so they can't use, I mean, there have been attempts to use the Clang compiler. We've tried to compile Linux with the Clang compiler. There are thousands and thousands of places in the code which are not ANSI standard C. We've got to go patch them. People have attempted to do this. We have never got it working. It's just a disaster. And I think that the moral of the story is write your stuff in ANSI standard C or C++. But you know, then you can use whatever compiler happens to be the best at whatever time. So for us to change from our own ACK compiler to Clang was a question of just changing the build system to call that compiler, and it works right out of the bat, off the bat. And Clang is a very nice compiler, has some very nice properties, which I'll talk about later, as well as producing very nice code. We adopted the NetBSD build system. We adopted the ELF file format. The whole source tree dealing with architectures is modeled on the way NetBSD does it. The headers and the libraries are all from NetBSD. It's got X11, you know, it's got package source. Last time I looked, we could build about 5,000 NetBSD packages right out of the box. You just say, you know, make, and everything happens right. Some of them don't work because we don't have some font library or there's some other thing. We didn't have the time to really track it down. But my guess is with a small amount of effort, you can probably get thousands more packages to work out of the box. You know, there's a few system calls we don't have. Those actually are impediments. But a lot of the stuff is sort of minor things, like some package needs some peculiar font we don't have, and it requires somebody to spend a day figuring out where the font is and how to install it. But a lot of stuff just works out of the box. And nevertheless, we've built Minix on top of, the NetBSD environment is built on top of Linux. NetBSD is built on top of the Minix environment. So there's some things we don't have. We don't have kernel threads. That's, long story, but in the beginning it wasn't there. It was too complicated. We have user land threads, but things that actually require kernel threads, that's a problem. There's some system calls that we're missing. Like we don't have the LWP calls, the message calls, SEM calls. Some might be easy to add. We don't have clone. We don't have some of the get and octal calls. We don't have KQ and Ktrace. Don't have vfork. We don't have job control, but it seems to me if you have X11, why would you want job control just under the window? And some minor calls are missing. Nevertheless, we can build over 5,000 packages, so it's, moderately close. If you're looking for a count of how close it is to NetBSD, there's the QA test. We ran all these tests, and 512 failed, and 2139 passed, and so basically 81% of the QA test passed. So it's sort of 81% of the way there, and the things that don't work tend to be the more exotic things. Okay, so it's not all the way there, and some of that requires some work, but we're a large way along, along the road there. So here's the system architecture. At the bottom line is, the bottom layer is the microkernel, okay, with the stuff running, that's the part that runs in kernel mode, it handles interrupts and loads the registers up and physically manages the page table and so on. Then the next layer is the drivers, all processes. Then come all the servers. All that's just Minix, okay? But in user land, we have packages and Clang and all that stuff, and that's NetBSD. So it's NetBSD sort of re-implemented on the Minix infrastructure with the reliability and self-healing properties of Minix, but to the user, it looks like NetBSD, okay? So we think this is kind of the best of at least two possible worlds. You have all the nice reliability properties of Minix, but you have a user interface which is familiar, at least to people who are, BSD people. Could we have done Linux? Maybe. Could it still be done? I think it would be hard because I don't think it's quite as clean as NetBSD. Okay, so here's Minix on the Beagle boards. Now, you can't read this, but green is good and red is bad. So
todavía falta, pero vamos a tratar de resumir hasta allí. Vamos a ver, ¿alguna pregunta, alguna duda? Términos nuevos, ya se sabían los términos. Carmen y mí.
Dígame, ingeniero.
Cuénteme, ¿qué comprendió?
Yo entendí sobre lo del kernel, de lo que hablaba ahí.
¿Algo más?
Sobre los tipos.
No le entendí. ¿De qué? Stalin.
Sí, aquí estoy, ya le dije. Un ratito es que hacen bulla a mis vecinos.
Ya, hasta que no hagan bulla, Stalin, martillo.
Sobre las características, sobre los ítems, el CPU, clocks, RAM, flash, video, GPI, pins, Ethernet, USB.
Pero eso es lo que está en pantalla, me está numerando lo que está en pantalla. Stalin, ¿qué comprendió hasta el momento? Stalin, se fueron a dormir. Perfecto. María Eloísa Bajaña,
Muy buenas noches, ingeniero.
buenas noches. ¿Qué comprendió?
Que estas personas estaban hablando sobre los estudios que habían hecho, sobre las investigaciones, sobre, daban unas fechas ahí, yo vi unas fechas que hablaban del software, del hardware, también hablaban de los drivers, de esas cosas, del kernel. Sí, no puedo apreciar mucho, pero más o menos ya me iba despertando lo que es el conocimiento.
Pero faltó despertar. Jocelyn Briones. Jocelyn.
Ahí se trató sobre cómo más o menos cómo iba evolucionando así las ediciones, o sea, hubo bastantes ediciones así entre libros así. O sea, fueron como los estudios basándose en cada etapa así.
¿Cuántas ediciones hubo?
Cuando una niña como yo hace una
¿Cuántas ediciones hubo? Se perdió. Steven, ¿qué comprendió? Steven Lino.
Se trató algo de algo de kernel y microkernel. Son servidores de software. Mencionaron que no son superusuarios.
No son superusuarios. ¿Qué son? ¿No son o son?
Mm, Mencionaban que no son superusuarios.
¿Y qué son? Jason, cuénteme, ¿qué comprendió?
Buenas noches.
Buenas noches.
Bueno, sí, bueno, yo al principio sí estaba viendo más o menos de lo que usted nos dio ayer, sobre lo que es el kernel, el microkernel, todo eso es lo que, bueno, como dice la compañera, lo que yo puedo apreciar es que hay una evolución eh, de todo, de cómo se ha desarrollado, más que también algo sobre el Windows, en qué año empezaba y que quisieron hacer una prueba, parece que me di cuenta ahí. Bueno, como trataba de leer también la parte de abajo,
Es que tiene
parece
que
que
leer la parte de abajo porque está la parte subtitulada. a menos que comprenda el inglés.
Por eso, pues, es que yo estoy del teléfono y estaba viéndole, a mí me sale en la parte de abajo por el subtitulado, pues tenía que estar leyendo eso. Eso es lo que yo más o menos le estaba entendiendo ahí.
Ya. Lenin, cuénteme, ¿qué comprendió?
Yo estaba más que todo viendo lo que era lo del Ring 3, que es User, el Ring 0, Linux, el Ring 1, que es Zen, etcétera. Ese tipo que es un sistema ligero. Eh, Más o menos también lo que era lo que se encontraba Minix en la CPU, dentro de la CPU, sino que así mismo lo mismo que pasaba con Jason, yo me desconecté de la PC como 3 veces, me salí, tuve que conectarme al teléfono y ahí se me dificultaba agrandar las letras para poder leer bien. Pero más o menos eso es lo que yo estaba leyendo, los anillos de privilegio, de ejecución, la jerarquía. Eso de ahí estaba tratando de
Habla de la
comprender
seguridad, de la confiabilidad del sistema
de la
operativo.
confiabilidad del sistema operativo, correcto, y lo ligero que es también.
Claro, es ligero y se lo pueden montar. Ahí estaba el Raspberry y lo que tienen en la claqueta, en la tabla, que es el Beagles, los Beagleboard, y aquí aparece algunos, el Beaglebone Black,
Medio leí algo de Media Engine, creo que medio leí eso, Media Engine,
Media
que
Engine.
puede ser utilizada, ajá, sino que puede ser utilizada con sus funciones.
Claro, ahí hay
Eso, ujú.
varias formas.
Accediendo a
Eh,
la memoria RAM.
claro, sí. Este, bueno, hicieron algunas pruebas, por lo que decía Andrew Tannenbaum. Lo interesante de lo que yo he visto, casi algunos, bueno, he visto dos grandes exponentes en vivo, entre comillas, y son bastante hiperactivos. Andrew Tannenbaum es bastante hiperactivo. Tiene que poner mucha atención porque habla rápido. Y así hay algunos que conozco que son exponentes en ciertas áreas, son especialistas y hablan muy rápido, son bastante hiperactivos. Ellos no pueden quedarse eh, sin perder el tiempo. Ellos siempre tienen que hacer algo, son bastante hiperactivos. Y Andrew Tannenbaum es igual. Él expresaba entre las últimas cosas, pues las pruebas que se hicieron, se ejecutó con un estudiante de él. Él es profesor tanto en la parte este, de la carrera universitaria como maestría y doctorado. Entonces tiene estudiantes en las tres áreas. Entonces uno de los estudiantes dice que aplicó un poco de código que se le montó al sistema operativo para poder ver si es que se este, podía corregir los errores, porque él habla de que un sistema operativo debe estar estable con cero errores y debe de autorrecuperarse ante un error. Entonces uno de los estudiantes puso 800.000 líneas de código en 100 pruebas. 100 pruebas se hicieron en total con 800.000 líneas de código que estaban dentro de las 100 pruebas. Y el 83%, poco más o menos, se pudo restablecer. O sea, tiene una confiabilidad alta en el sistema operativo Minix. Y es bastante ligero, se le puede poner en el Beaglebone Black, que aparece en la claqueta, como en el Beaglebone White y el Beagleboard. El Beagleboard parece ser que es un poco mejor que el Raspberry. Pueden entrar a la página. La página la tenía,
Una
es,
pregunta, pero yo alcancé a leer ahí en el subtitulado que él creó el programa, era solo como para dar impartir una clase de sistema operativo. No,
claro,
no lo había creado como en términos comerciales, o sea, él no pensó en
no,
este caso en parte comercial, sino como para docencia.
claro, es así. Es que por eso es abierto. Todo lo que ha creado es netamente para docente porque él es profesor. Entonces, toda su investigación se basó en esa línea, en la línea de investigación, en la línea de docencia. Entonces, la maestría, los doctorados en la cual estuvo a cargo, él tiene bastante conocimiento de los sistemas operativos. Por eso inicialmente en la clase arrancó con una cuña negra hacia Windows. Y es verdad lo que dijo. Entonces, después de tantas cosas que le meten, anti-spamware, anti-spam, etcétera, 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 pues el sistema operativo sigue igual, con errores, después de tantos parches y toda la cosa. Entonces, por eso él dice que el sistema operativo tiene que autorrecuperarse solito de los errores. Entonces, por eso él trata de reducir al máximo el número de líneas para que quede de la forma más básica, dándole la seguridad del caso. Por eso hablaba en una parte de la confiabilidad y la seguridad del sistema operativo. Y ahí es que empezó a hablar de las pruebas. Entonces, ustedes pueden montar aparentemente con toda seguridad para que los aplicativos no puedan entrar a, a los datos, al bloque de datos, al bloque de instrucciones del otro aplicativo. Porque en medio de la comunicación entre los procesos va a estar el microkernel. O sea, el microkernel va a ser el árbitro de eso. Si bien es cierto, todos los servicios no están montados allí, pero él funge de árbitro hacia los servicios, sistemas de archivos, servidores de archivos, etcétera, etcétera, etcétera. Entonces, el proceso se comunica, le envía un mensaje al microkernel y el microkernel da el paso para que entren para allá. O sea, toda la gestión la va a hacer el microkernel, no está aislada. No es que directamente entran a los servicios, sino que las capas están separadas, pero el mensaje va hacia el microkernel y de ahí sube. Por eso vieron algunas gráficas con respecto a eso, de cómo entraba la comunicación ahí, cuando había errores, cuando no estaba en caché o cuando estaba en caché. Entonces ahí hablaba cuando no estaba en caché el error, porque cuando está en caché no importa. Entonces hace las peticiones a las diferentes capas de servicios, llega al microkernel y si está, pues no importa, regresa. Pero ¿qué ocurría cuando no estaba en caché, no estaba cachado? O sea, ya salía de la RAM y lo mandaban a disco. ¿Y qué pasaba en eso? Pues también se explicó aquello. ¿Qué más? Bueno, hasta aquí nos vamos a quedar. Ya el premio, digo, el tiempo apremia. En la próxima clase les voy a tomar esto. Normalmente no les digo que les voy a tomar, pero ahorita sí les voy a decir que esto va a ser lección oral para la próxima clase. Así que revisen bien la conferencia de Andrew Tannenbaum con Minix 3. Eso sería todo por mi parte. Excelente tarde, bueno, excelente noche, perdón. Que Dios los bendiga, que Dios los guarde. Pasen bien.
Gracias, ingeniero.